Hello, I'm an old guy and I do maths. Today we're going to look at lines of best fit, how they are calculated. Notice I didn't say how we calculate them, how they are calculated. And in particular, we're going to look at least squares regression. Now, I'm going to show you the formula for how this is actually done. And I don't want you to be put off by this because 99% of people who do this use a calculator to do it. Probably the majority of those people use either a Texas Instruments calculator or a Casio ClassPad or Casio calculator to do this. And really, I just want to lift the lid a tiny bit on what goes on inside that calculator and then demonstrate what's really involved in calculating a line of best fit using a least squares regression. Just show you what the effect of it is, so that I guess what this video is about is it's about understanding a little bit of what goes on, which makes understanding least squares regressions all that bit easier. Okay, so essentially we're calculating a line, which means we get a linear equation. And so we have to calculate two things. We have to calculate gradient, and please note this warning, do not be put off by this. You don't have to do this. This is what goes on inside your calculator. Basically, this horrible looking thing here is a fairly fancy gradient calculation using all the data that's available in both the X and Y columns as you enter it in your calculator. That's really all I want to say. It's a glorified form of y2 minus y1 over x2 minus x1. It's just a gradient calculation. The other thing, of course, that you have to find is you have to find the y-intercept, usually referred to as c. And mind you, if you're using a calculator, this will be referred to as a probably, and this will be referred to as b, because your equation will be in the form of y equals a plus bx. The standard for years has been y equals mx plus c, which I've got written down here. Now, this is the formula for calculating c. Now, what I want you to take away from this is that what your calculator does is it calculates a gradient and it calculates a y-intercept. And you don't need to know the magic of this. What you do need to understand is, in practical terms, what it does. And so I've got a couple of fairly simple scatter plots here. One's much simpler than the other. This is the difficult one. This is the complicated one. So what I want you to imagine is that you've got a graph like this with a scatter plot on it without this line. This is our regression line. And essentially what your calculator is trying to do is it's trying to equate the differences above this line, between the line and these points, with the distances and the differences below the line. And it's trying to get this line to a point where the difference between all the distances from the line to these data points is equal to the distance from the line to all of these data points. And that's essentially what getting a regression line is all about. It's about getting the best possible fit, which means reducing the distance, the total distance of all these points from this line to as near as you can possibly get to the total distance from the line to these points. These distances, of course, are called residuals, and there's a video on those. Now, let's simplify this greatly. So we have three data points here, and these are the actual data points. And if we draw our regression line, as we are pretending it's calculated by a calculator, it might look something like that. And what you'll notice is that the regression line passes through one of these points, which means that the distance from the point to the line is 0. And if we contemplate this distance for a moment and this distance for a moment, what we find is, hopefully, if I've drawn this anyway near correctly, that this distance is approximately the same as this distance. That's my intention anyway. And so the ideal regression line, if we have these 3 points of data, is that this distance is the same as this distance. Now, this is an exaggeration because, quite frankly, the line should probably be like that. It should probably be much closer to these 2 points, but this is just drawn to exaggerate the point. And what your calculator does is it figures out that distance, gets them to be as equal as possible, but you have to remember that there would be many other pieces of data. So we just assume, I think we just assume for the purposes of this demonstration, that this is just a very small part of something like this. But that's essentially the process. So a least squares regression line is an attempt to minimize the distance between a regression line and as many of the data points above it and below it as possible. And so you can see how many calculations would be involved here. There's a good reason that this is done on a calculator usually. So it would be trying to make sure that, basically, to put it simply, and this is putting it crudely, it's not exactly what happens, the sum of all of these distances and differences is equal to the sum of all of these. And when that is achieved, you have a least squared regression line. Thank you for watching this. Please remember that not even in your worst nightmares, I imagine, will you be required to perform this operation. It's mostly calculator based, and what I really wanted to demonstrate is roughly how it's done and the effect of it, so that when you hear someone talking about a least squares regression line, you've got an idea of what's going on. Anyway, thank you very much for watching. If you found this useful, please subscribe. There is a playlist devoted to this sort of thing. It's got things like residuals in it, and R and R squared, all of the things that you see when you're dealing with statistics. Anyway, I'll see you on the next video. Don't forget to like and subscribe. Thanks. Bye.